Hello everybody, Mr. Troy here. I've got another video for you in our pre-calculus series. This is Unit 1, Polynomial Functions, and we are in Lesson 5, Rational Zeros. Our essential question today is how do you use the rational zero test to find possible zeros of a polynomial function? Okay, our starting point here is what is a rational number? Give examples. A rational number is a number that is the ratio of two integers. So for example, 3/2 is 3 over 2, 7 is 7 over 1, and -1/3 is -1 over 3. So what you think of as proper and improper fractions, and also the counting numbers. 0 counts as a rational number as well. We have a hierarchy or taxonomy of numbers. All numbers are complex numbers, and complex numbers are made up of real numbers and imaginary numbers. Inside real numbers, numbers can be rational or irrational. And a rational number might also be an integer or a whole number or a natural number. So a natural number is 1, 2, 3, and the like. A whole number is 0, 1, 2, 3, and the like. And the integers are things like -3, -2, -1, 0, 1, 2, 3, and so on. Remember, rational numbers are things like 7/2. Irrational numbers are things like the square root of 2. Okay, here's what the rational zero test, or the rational roots theorem, has to say. If the polynomial f of x has integer coefficients, then every rational zero of f of x has the form plus or minus p over q, where p is a factor of the constant term and q is a factor of the lead coefficient. I'm going to do a very quick example here. If we look at a quadratic function, we can see that some of the rules for factoring come from that number 6, some of the things that might be factors. And some of the other information about what might be a factor comes from the 2, the lead coefficient. So while this factorization shown is not correct, there is at least a degree of reasonableness to it. It makes sense to have a 2x, and it makes sense to be using 2 and 3. This factorization, on the other hand, is completely unreasonable. Why would I use a 5x and or a 3x to try and make a 2x squared? And why would I use a 7 or a -5 to multiply to make 6? It just doesn't make sense. Taking a look at another example, 2x plus 3 and x plus 2 are reasonable factors for 2x squared plus 5x plus 6. It makes sense to have a 2x and an x, and it makes sense to have a 3 and a 2. Now in this case, there actually is no factorization for 2x squared plus 5x plus 6, but I just wanted to make the point that some things are reasonable and some things are unreasonable. That's an actual word. So our possible rational zeros are factors of our constant over factors of our leading coefficient. So let's take a look at something that actually does factor. 3x squared minus 10x plus 3. The way that this factors is to 3x minus 1 and x minus 3. And the zeros that come out of that would be 1/3 or 3. Now 3 would be 3 over 1 to make you think of a rational number. And you see how those are factors of 3 in the numerator and the other 3 in the denominator. That's where this possible rational zero test comes from. So if I'm trying to find all of the possible rational zeros for a given function, what I'm trying to do is I'm trying to say, what are the sort of things that I would like to do synthetic division on? What are some things that make sense to try if I have to guess and check? So the pattern is factors of the constant term over factors of the lead coefficient, and all of the different patterns that come out of that, all of the different possibilities. Because of all the different possibilities there are, I like to list them. I use an array like this, and I just simply simplify each one. So 8 over 4 is 2, 8 over 2 is 4, and 8 over 1 is 8. 4 over 4 is 1. 4 over 2 is 2, but I already listed that, so I don't need to list it again. And 4 over 1 is 4, but again, I already listed that, so I don't need to list it again. 2 over 4 is 1/2. 2 over 2 is 1, but I've listed that already. And 2 over 1 is 2, but again, I've listed that already. 1 over 4 is 1/4. 1 over 2 is 1/2, but that's already listed. And 1 over 1 is 1, but that's already listed. So these numbers right here are all of the possible things that could be zeros of this polynomial function. So I'm going to list them. Either positive or negative 8, 4, 2, 1, 1/2, and 1/4. All right, pause the video and try the next one on your own. All right, so the pattern here is factors of 4 divided by factors of 6. Since I'm going to use the plus or minus, I don't have to write factors of -4. I can just say factors of 4. I'm going to set up this array. And what am I going to do with that? Do you remember? Well, I'm going to take the fraction or the ratio of all of those numbers. And all of those answers are my possible rational zeros. Notice I crossed off the ones that were repeats. So here are all of the possible numbers that could be a zero of the function. So what this means is it is possible that if I plug in 4 to the function, I might get 0. It is possible that if I plug in, say, -1/3 to the function, I might get 0. But it's not possible that if I plug in 3, I will get 0. I know this seems like a small thing, but before doing this problem, any number might have been a 0. Once we know that there are only a handful of numbers to look for, we've cut it down from infinity to however big that handful is. So once you've done the rational zero test, you're going to want to eliminate some possible zeros. There are 3 ways you can do that. You might do that by using substitution. You might do that by using synthetic division, or you might do that by looking at a graph. Here, when we say substitution, we mean just plugging it in directly. If you don't have a graph, your fastest way to go is by using synthetic division. All right, here's an ordered list of things that you want to do to find zeros of a polynomial function. The first thing that you want to do is to look for a GCF, and if you can, factor the polynomial. If that doesn't work, you want to then next find all possible rational zeros like we just did. So for our problem on the side, I've listed all possible rational zeros, factors of 8 over factors of 1. Then you want to use a graph, synthetic division, or substitution to find a 0, but you probably want to use synthetic division. One thing that's important to remember is that this is a guess and check process. My first guess might not be correct. So, for example, I would probably want to start with smaller numbers. If I plug in 1, I think I find pretty quickly that it doesn't work. I get this remainder of 6. That's okay. I just know that -1 doesn't work. Cross it off the list and give it another try. So now, after trying 1 and finding that it didn't work, I'm going to try -1 and see if it does work. I'm using the smaller numbers because that's easier to do. So when I plug in -1 and I multiply, I find that I get a remainder of 0. So you want to use synthetic division to find the 0 and then use synthetic division to break down the polynomial. Now what does that mean? Well, it means to write it as whatever the quotient is. So in this case, it would be x squared minus 6x plus 8. Now you want to repeat steps 2 and 3 until the, steps 3 and 4 until the polynomial is broken down to a quadratic. Once you have a quadratic, you can use factoring or the quadratic formula to find the remaining zeros. Then you want to provide your answer in the correct form. The reason this is highlighted is because some questions will ask you for zeros and some questions will ask you for factors. Okay, so problem 3 says we're going to find all of the real zeros of a polynomial function. Now let's not let this problem fool us. Just because we know the rational zero test doesn't mean we always have to use it. This problem, you may notice, can be factored by grouping. If that's true, I don't need to do the rational zero test at all. So I can come up with a factorization of a linear and a quadratic, and I can completely factor that. No reason to do the rational zero test at all. My zeros are -3, -2, and +3. Easy peasy, as the kids say. Now, this next problem does not factor. I could go through the trouble of trying to see it, but there's not a pattern that exists between x to the 4th minus 9x squared and 4x and 12, or -4x and 12, as the case may be. So I'm going to look at all of my possible rational zeros. Remember, that's plus or minus factors of 12 over factors of 1. I love it when one of my coefficients is 1, because that means I have much, much less work. So my possible rational zeros are plus or minus 12, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, and plus or minus 1. I'm always going to start by plugging in 1. So I'm going to set up my synthetic division. And I'm going to see if 1 works. Well, that's just great news. It does work. So one of my zeros is 1. And I'm left with x cubed plus x squared minus 8x minus 12. Now, just because one of my zeros has been used once doesn't mean that it couldn't repeat. So I'm going to move that off to the side, and I'm going to see if maybe 1 still works. You never know, right? So remember, when you're doing synthetic division a second time or a third time, you can just use those same coefficients. And I can kind of see as I'm coming here that it's not going to work. I get a remainder of negative 18. So all's not lost. I can note that 1 doesn't work. And I can try negative 1. Negative 1 does not work as well. So where do I go from here? Well, my personal preference is to use small numbers whenever possible. So I'm going to try 2, then negative 2, so on and so forth. Well, I tried 2 and it didn't work. This is why I suggest using synthetic division, because it's so much faster. Now I'm going to go back and I'm going to try negative 2. And like I said, you just keep trying until you have something. Sorry, I had to clean that up a little. Now, as you can see, when you plug in negative 2, it works. So what we have found is that so far we have factored x minus 1 and x plus 2 out. And we are left with x squared minus x minus 6. Now that's a quadratic, so I can just factor that. And I get x minus 3 times x plus 2. Another way to write that complete factorization would be x minus 3 times x minus 1 times x plus 2 squared, because it appears twice. So my zeros are 1, 3, and negative 2. Now that 0 that was repeated is said to have what's called multiplicity of 2. It counts twice. The factor appears twice when you multiply, but you don't really need to say the 0 multiple times. You don't need to say, well, 3 works and 1 works and negative 2 works and negative 2 works. Too much. So what does it mean when something has multiplicity of 2? Well, in that case, instead of going through in either way, the graph would bounce. It bounces off the x-axis, just, the same way that x squared bounces off the x-axis, from Algebra 1. When something has multiplicity 1, it passes through, similar to the way that a line would. And when something has odd multiplicity of like 3 or 5 or 7, it is going to squiggle through. So it will look something like this. All right, for this final problem, I'm going to start by listing all of the possible rational zeros because I know it doesn't factor. Okay, so I've listed all of my possible zeros. I've already shown you plugging in things like 1 and 2 for a while, so I think I'll plug in a fraction. So I'm going to plug in 1/2. We haven't seen a fraction yet. So as I do this, you will see that the numbers actually stay relatively okay. I don't get any crazy fractions in here, although sometimes that does happen. Now, 1/2 was a 0. So one of our possible zeros, or one of our actual zeros, we'll list it is 1/2. But this would mean that x minus 1/2 was a factor. And we don't normally think of a factor as being x minus 1/2. Our factors always have whole numbers in them. So our factor is actually going to be 2x minus 1. That's what gives us that 0 of 1/2. Which means this quadratic here isn't 12x squared plus 10x minus 12. We actually have to divide by 2. And we get 6x squared plus 5x minus 6, which we can either factor or we can use the quadratic formula. So this factors into 2x plus 3 times 3x minus 2. So our other zeros are -3/2 and 2/3. Our complete factorization is those things times 2x minus 1. All right, I hope that's helpful. Thanks for watching.